Morning, everyone. My name is Talitha Azzahra Kirana from the Faculty of Engineering, Universitas Indonesia. Today, I will present my study entitled Origin Destination Matrix Estimation based on travel time observation. This research explores whether observed interzonal travel time can be used as a practical basis for estimating an origin destination matrix or OD matrix in an urban road network. The case study is in the Danau Sunter area in North Jakarta. Origin destination matrices are essential in transport planning because they describe trip distribution between zones and directly affect traffic assignment results. However, conventional audio surveys are often expensive, time-consuming, and difficult to update, especially in dynamic urban environment. For that reason, this study considers a more practical alternative. Instead of relying on conventional audio survey data, the study used observed travel time because travel time reflects the operational outcome of travel demand interacting with network characteristics. Based on that idea, this research asks whether interzonal travel times from Google Maps can support odometric estimation in a corridor-scale urban network. The objective of this study is to estimate an OD matrix that, when assigned to the network, produces model interzonal travel times consistent with the observed travel times. The analysis focuses on the Danau Sunter area in North Jakarta, represented by a simplified network of 96 links and 8 analysis zones, or we call it as Transport Analysis Zone or TAZ. The base demand was obtained from the simplified 2019 Jabodetabek transport model. The observed variable was centroid to centroid travel time collected from Google Maps during the peak period, specifically on Tuesday, 12 May at 9 a.m. In this framework, the passenger car matrix was updated iteratively while non-car demand was treated as preload demand. This slide summarizes the methodological sequence. First, the analysis starts with the prior OD matrix and simplify the road network. Second, the matrix is assigned using user equilibrium together with a link performance function. Third, modeled interzonal travel times are extracted. Fourth, those modeled travel times are compared with the observed travel times. Based on the comparison, the OD flows are updated using relative error information and a selected step size. The procedure is then repeated until the relative change in OD travel time between two successive iterations falls below 5%. In this study, only passenger car demand was updated iteratively, while motorcycle and other good vehicles matrices remain as preload demand in the network assignment. For traffic assignment, the study used the user equilibrium to represent congested urban traffic condition. Link travel time is represented by BPR or Bureau of Public Roads using standard parameter values of alpha equals to 0.15 and beta equals to 4. After assignment, the modeled OD travel time are compared with the observed OD travel time. Then each OD pair is adjusted in proportion to the normalized difference between the modeled and the observed travel times. In other words, if the assigned travel time is still not consistent with the observation, the OD flow is updated and reassigned. This iterative process continues until the convergence criterion is satisfied. The best model was developed from the regional Jabodetabek transport model and then converted into a smaller model tailored to the Danau Sunter area boundary. This conversion involves simplifying both the road network and the OD matrix while preserving the essential structural characteristic of the original regional model. To maintain this influence of trips interacting with the study area, a dummy node was introduced at the outer boundary. This treatment allows the simplified model to retain movement entering, leaving, or passing through the network. The converted model then serves as the basis for the traffic assignment and iterative order matrix estimation. The estimation procedure was implemented in Cube. In each iteration, the updated order matrix was reassigned to the network in order to generate a new set of model travel time for the next evaluation cycle. The workflow therefore consists of traffic assignment, travel time extraction, error calculation, and matrix updating within a repeated loop. Through this process, the OD metric was progressively adjusted toward a better fit with the observed travel time matrix. This is important because the study does not attempt to replace the prior matrix directly, but rather to calibrate it using observed network performance as the reference. This slide presents the change in total trips between the initial and final order matrix. In general, OD values increase across the iteration. This indicates that the initial metric tended to underestimate the level of demand required to reproduce the observed network condition. The final metrics can therefore be interpreted as the calibrated demand pattern that satisfies the convergence criterion within the study framework. To illustrate the convergence, the paper presents 5 sample OD pairs: 4 to 7, 7 to 4, 7 to 8, 8 to 6, and 8 to 7. The results shows that travel times change more noticeably in the early iteration and then become more stable in the later stage. In other words, the difference between iteration n and iteration n plus 1 become progressively smaller. These changes remain below the 5% threshold, indicating that the iterative updating process achieved the study's convergence criterion. This pattern demonstrates that the procedure was able to produce stable model travel times through the repeated updating cycle. Although the final assigned audit travel time remained lower than the observed travel time overall, the results still show a reasonable level of agreement for a substantial share of the matrix. Specifically, 48% of audit travel time pairs achieve difference of less than 25% from the observed values. The study identifies 3 main reasons for the remaining difference. First, the model is used simplified network, while Google Maps reflects a more detailed road representation. Second, the assignment applies standard PPR parameters, which may not fully represent Jabodetabek traffic condition. Third, the study area is relatively small and has limited route alternative, making OD travel time sensitive to minor road or link time changes. In conclusion, the studies show that observed interzonal travel time can be used as a practical basis for odometric estimation in an urban road network. In the Danau Sunter case study, the combination of Google Maps travel time observation, a simplified Jabodetabek-based model, and iterative OD updating improved the consistency between modeled and observed network performance. The convergent pattern also demonstrates that the procedure was capable of producing stable travel time results and calibrated OD metrics for corridor scale analysis. Overall, these findings highlight the methodological potential of travel time-based OD estimation as a more adaptive and operationally efficient alternative to conventional audio survey approaches. For future research, three improvements are recommended. First, the network representation should be developed with a greater level of detail, so that it more closely reflects the road structure represented in Google Maps. Second, the BPR parameters value, especially alpha and beta, should be calibrated to better represent urban traffic conditions. And last, the proposed methodology should be tested on a larger study area, together with further refinement of the observation framework and validation strategy, in order to better understand the method's sensitivity under broader network conditions. Thank you very much for your attention. I would be happy to receive any question or suggestion. Thank you.